Look up at the night sky. What you see is a tapestry of light, a scattering of brilliant stars against the velvety darkness. It feels full, almost crowded with distant suns and swirling galaxies. But this is an illusion, a beautiful trick of perspective. The truth is, space is mostly nothing, a profound and staggering emptiness that stretches for billions of light years. We are tiny specks living in the thin, glowing threads of a cosmic web, surrounded by an ocean of void. But what if I told you that within that immense nothingness, there are regions of emptiness so vast, so fundamentally empty, that they defy our basic understanding of the universe? Astronomers call them supervoids, and the largest one ever discovered isn't just an empty space. It's a place where the very rules of reality seem to bend. A place where, according to some incredible theories, the flow of time itself might be altered. This isn't science fiction. This is a frontier of modern cosmology, a genuine mystery written into the fabric of the cosmos. We are about to go on a journey to the edge of the known, to a patch of sky so strangely quiet it has left scientists questioning the foundations of physics. This is the story of the supervoid that seems to warp time, a celestial enigma that challenges everything we think we know about the universe. Imagine a hole in reality so large that it could swallow thousands of galaxies, a cold spot in the cosmos where the afterglow of the Big Bang itself looks different. What could create such a structure, and more importantly, what bizarre effects is it having on the space-time within it? The answers are as profound as they are unsettling, pointing to forces and principles we are only beginning to grasp. So get ready to peer into the greatest emptiness we have ever found, and to explore how this colossal nothing might be quietly, subtly, changing the way time passes for everything inside it. To truly grasp the scale of a cosmic supervoid, we first need to shift our perspective on what the universe looks like on its grandest level. We often picture galaxies scattered evenly throughout space like stars in the night sky, but that's not the case. Instead, the cosmos is structured like a colossal sponge or a vast cosmic web. The bright, glowing strands of this web are galaxy filaments, immense walls made of thousands of galaxies bound together by gravity. Where these filaments intersect, you find dense, brilliant knots known as galaxy clusters, the most crowded cities in the universe, and between these structures, there are the voids. These are the empty bubbles in the cosmic foam, the great deserts of intergalactic space. A typical void might be tens of millions of light years across, already a size so immense it's difficult to fathom. But a supervoid is something else entirely. It is the king of these empty spaces, a region so disproportionately vast and empty that it can span 500 million, even a billion light years. Within a volume of space that could comfortably contain tens of thousands of galaxies, you might find only a handful or perhaps none at all. This isn't just an empty room in the house of the universe, it's a missing wing the size of a continent. The sheer scale of nothingness is what defines it. This emptiness has profound physical consequences because there is so little matter, so few galaxies, and so little dark matter. The gravitational landscape inside a supervoid is fundamentally different. It's a place of weakened gravity, a cosmic hill that has been excavated to an extreme degree. And as we'll soon discover, it's this very lack of stuff, this incredible deficit of matter and energy, that might be causing some very strange things to happen to the fabric of space and time within its borders. Our story begins not with a telescope pointed at darkness, but with a map of the universe's first light. This is the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. It's the oldest fossil in the cosmos, a snapshot from when the universe was just 380,000 years old, cooling from a hot, dense plasma into a transparent gas. This relic radiation fills all of space, and it's incredibly uniform, a nearly perfect blanket of microwave heat that sits at a frigid 2.7 degrees above absolute zero. But if you look closely, you see tiny, random variations, ripples of slightly warmer and slightly colder spots. These ripples are the seeds of all future structure, the gravitational blueprints for the galaxies and voids we see today. They are supposed to follow a predictable statistical pattern. So when NASA Wilkinson Microwave Anisotropy Probe, or WMAP, finished its detailed all-sky map of this background in 2003, scientists began sifting through the data, expecting to confirm our standard models of cosmic evolution. What they found instead, in a particular patch of the southern sky near the constellation Eridanus, was an anomaly that sent a ripple of its own through the world of cosmology. It was a cold spot, but this wasn't just any slight fluctuation. It was enormous, spanning a vast area of the sky, and it was significantly colder than our models said it should be. The probability of such a large and cold region appearing by pure chance in our standard model of the universe was astronomically low, less than 1 in 100. This was a glaring outlier, a cosmic bruise that didn't seem to fit the otherwise beautiful picture. The initial reaction was a mixture of excitement and skepticism. Could it be an error, an artifact of the way the data was processed, or was it a foreground object within our own galaxy casting a shadow? Each of these possibilities was investigated and one by one ruled out. The cold spot was real, and it was a feature of the deep universe. A decade later, the European Space Agency's Planck satellite, with even higher resolution and sensitivity, confirmed the WMAP finding in stunning detail. The Planck map showed the cold spot in all its puzzling glory, deepening the mystery. This left cosmologists with a pressing question: what in the universe could possibly create such a profound cold spot on the CMB? The most straightforward explanation, and the one that quickly gained traction, connected this ancient signal to a modern cosmic structure. The hypothesis was that between us and this patch of the CMB, there lies a truly enormous region of space, a supervoid. The theory rests on a fascinating and somewhat counterintuitive concept in cosmology known as the integrated Sachs-Wolf effect. Here's how it works. As light travels through the universe, it climbs in and out of gravitational wells. Think of a photon of CMB light traveling for over 13 billion years to reach our telescopes. If it passes through a region with strong gravity, like a galaxy cluster, it must expend energy to climb out of that gravitational pit. This energy loss causes it to become slightly redshifted, appearing a tiny bit colder to us. Conversely, if it falls into a void, a region of weakened gravity, it doesn't lose as much energy. When it climbs out, it actually gains a small amount of energy, making it appear slightly hotter. But this simple picture changes if the universe is not just expanding, but if that expansion is accelerating due to dark energy. In an accelerating universe, the gravitational landscapes themselves are changing over cosmic time. A supervoid is not just a static hole, it is becoming shallower as the universe expands. So when a CMB photon enters a supervoid, it initially gains energy as it falls in. But by the time it leaves, the gravitational hill it has to climb is less steep than when it entered. This means it doesn't lose all the energy it gained. The photon arrives at our detectors with a net gain of energy, making it appear hotter. This is the late-time integrated Sachs-Wolf effect. So, if a supervoid should make the CMB look hotter, why are we seeing a cold spot? This is the beautiful twist that makes the Eridanus Supervoid so compelling. The leading idea suggests that the sheer, staggering size of the void is the key. The gravitational effect of a typical small void is minuscule, but a supervoid spanning nearly 2 billion light-years is so vast that the photon is inside it for an immense amount of time, and the cosmological effects are magnified. Some theories propose that the very expansion of space within the void, combined with its profound emptiness, could lead to a different, more dominant effect that actually removes energy from the light, causing the observed cooling. It's as if the light gets tired from traveling through such an immense nothingness. The discovery of the cold spot, therefore, wasn't just the discovery of a strange temperature reading. It was the trigger for a cosmic detective story, one that pointed toward the existence of one of the largest structures in the universe, a structure defined not by what is there, but by what is missing. So the plot thickens. We have this enormous cold spot on the ancient cosmic background radiation, and we have a theoretical suspect, a supervoid. But how exactly does an immense region of nothingness make the light from the Big Bang appear colder? The bridge between these two discoveries is one of the most elegant ideas in modern cosmology, a phenomenon known as the integrated Sachs-Wolf effect. To understand it, let's think about light not just as a wave, but as a traveler on an epic journey across an ever-changing landscape. A photon from the cosmic microwave background has been flying towards us for over 13 billion years. Throughout that unimaginable voyage, it doesn't travel through a static universe. It's navigating a cosmic topography that's constantly evolving, full of gravity wells and hills. Now imagine this photon approaching a supervoid. A void is a region of weakened gravity, a cosmological hill. As the photon falls into this vast emptiness, it's actually climbing out of the denser universe around it. In doing so, it loses a little bit of energy, which causes it to redshift slightly. This is the first part of the story, but in a universe where the expansion is accelerating due to dark energy, something extra happens. The gravitational landscape itself isn't fixed. That supervoid is getting even emptier, its gravitational hill becoming shallower over cosmic time. So when our CMB photon finally reaches the far side of the void and begins to climb out, the hill it has to ascend is not as steep as the one it descended on the way in. Because the climb out is easier, the photon doesn't get as much of a gravitational redshift as it otherwise would. It effectively holds onto a little more of its energy. In a standard, non-accelerating universe, the energy lost falling in and the energy gained climbing out would perfectly cancel. The photon would arrive at our telescope looking exactly as it should. But in our dark energy-dominated reality, they don't cancel. The photon gets a tiny net boost in energy, making it appear slightly hotter, not colder. This is the standard late-time integrated Sachs-Wolf effect. So we're left with a puzzle. If a supervoid should make the CMB look hotter, why is the Eridanus spot so profoundly cold? This is where the sheer, staggering scale of the proposed supervoid comes into play. We're not talking about a small empty patch. This hypothetical void is thought to be so cosmically vast, perhaps over 1 billion light-years across, that the simple model might break down. When a structure reaches this immense size, it stops being a mere feature within the universe and starts to influence the fabric of space-time on a fundamental level. Some cosmologists propose that the incredible underdensity of the supervoid creates a unique gravitational redshift effect that dominates over the standard ISW heating. As light travels through this billion light-year expanse of near-total emptiness, the cumulative effect of the weakened gravity could actually cause the light to lose more energy overall. It's as if the light is on a long, slow, uphill trek the entire time, gradually bleeding energy and becoming redder and colder. Another, even more mind-bending possibility involves something called the Rees-Simon effect. This is a more complex version of the story where the supervoid isn't just sitting there passively, it's actively evolving. If the void is still in the process of forming, with matter being pulled out of it and onto its dense surrounding ridges, the changing gravitational potential can impart an additional net redshift to any light passing through. Think of it like this: you're rolling a marble across a rubber sheet that is simultaneously being stretched. The marble loses energy not just from the shape of the sheet, but from the fact that the sheet itself is deforming under it. In this scenario, the combined and amplified effects within a supervoid of such phenomenal scale could theoretically result in the significant energy loss needed to create the cold spot we observe. So the cold spot becomes a kind of cosmic signature, the shadow cast by the greatest emptiness we know. It's a fossil imprint of a structure so large it can alter the journey of primordial light, a testament to the fact that in the cosmos, nothing can be just as powerful and influential as something. The hunt was on, with the cold spot confirmed as a real and profound anomaly. Astronomers turned their telescopes toward that specific patch of the southern sky, searching for the physical structure that could be casting this cosmic shadow. What they found was both breathtaking and baffling. Stretching across an almost unimaginable expanse, centered roughly in the direction of the constellation Eridanus, lies a region of space so empty it redefines the word. This is the Eridanus Supervoid, a cosmic desert of staggering proportions. Current estimates suggest it spans nearly 2 billion light-years from one edge to the other. To put that into perspective, if you could travel at the speed of light, it would take you 2 billion years just to cross this single area of nothingness. Our entire Milky Way galaxy, with its 100 billion stars, would be a mere speck in this vast emptiness, a single grain of sand in a void the size of the Sahara. The significance of this discovery cannot be overstated. Before the Eridanus Supervoid was identified, our maps of the large-scale structure of the universe had voids, yes, but nothing on this scale. Finding a structure this enormous pushed the limits of what our standard cosmological models, the very models that describe how the universe evolved after the Big Bang, thought was possible. It exists right on the edge of statistical plausibility. You see, in the early universe, slight quantum fluctuations were stretched to enormous sizes by a period of rapid expansion called inflation. These fluctuations became the seeds for all future structures. Our models predict a certain maximum size for these seeds, which in turn predicts a maximum practical size for things like galaxy clusters and voids. The Eridanus Supervoid brushes right up against and may even exceed that predicted maximum size. Its discovery forced cosmologists to re-examine their assumptions. Was there something special about the initial conditions of the universe in this region? Could our understanding of inflation be incomplete? Or does the existence of such a colossal void hint at an even more exotic explanation? It became a living laboratory, a natural experiment on a billion light-year scale, testing the limits of our most fundamental theories. Its location is also key. Sitting directly along our line of sight to the cosmic microwave background cold spot, it provides the missing link between the ancient light and the modern universe. It's the lens, the filter, the immense cosmic feature that is actively altering the light passing through it. Finding it transformed the cold spot from a mere statistical curiosity into a tangible, physical phenomenon. We weren't just looking at a temperature anomaly on a map. We were seeing the direct consequence of one of the largest single structures ever identified, a structure whose profound emptiness creates effects we are only just beginning to understand. But to truly understand the bizarre power of this supervoid, we need to dive deeper than just the journey of light. We need to consider the very stage upon which that journey takes place, the fabric of spacetime itself. And for that, we turn to the revolutionary vision of Albert Einstein. His theory of general relativity completely reshaped our understanding of gravity. It tells us that gravity is not a mysterious force pulling objects together, but rather a curvature of the four-dimensional fabric of the universe, a combination of space and time. Think of spacetime as a vast, flexible trampoline. Place a heavy object like a bowling ball in the center, and it creates a deep dimple. This is what a massive object like a star or a galaxy does. It warps the spacetime around it, and this curvature is what we experience as gravity. Smaller objects like marbles will naturally roll toward the bowling ball, not because of a force, but because they are following the curved path of the trampoline surface. Now imagine the opposite scenario. What happens if you don't place a bowling ball on the trampoline, but instead you carefully lift a large section of the fabric upward, creating a broad, gentle hill? This is the gravitational landscape of a supervoid. It is a region of incredibly low density, a deficit of matter. In Einstein's universe, this lack of mass creates a correspondingly shallow gravitational potential, a broad cosmic hill instead of a deep well. The spacetime within the void is less curved than the spacetime in the crowded, dense universe outside of it. This difference in curvature is the key to everything. For a photon of light traveling through this landscape, the path is anything but straight. As it enters the supervoid, it is moving from a region of steeper curvature into a region of flatter curvature. When it eventually exits, it must move back into the steeper curvature of the dense external universe. In a static universe, the energy lost on the way in would be perfectly regained on the way out. But our universe is not static. It is expanding at an accelerating rate driven by the mysterious influence of dark energy. This acceleration changes the rules of the game. The gravitational landscape is actively changing while the photon is in transit. The supervoid, already a hill, is becoming an even shallower hill as the universe expands. So when the photon finishes its billion-year trek across the void and goes to climb back out, the hill it has to climb is less steep than it was when the photon first entered. This results in a net gain of energy for the photon, which we've discussed as the integrated Sachs-Wolf effect. But for a void of this staggering scale, the effect isn't just on photons, it's on time itself. According to general relativity, gravity doesn't just bend space, it also warps time. The phenomenon is called gravitational time dilation. A clock in a strong gravitational field, like near a black hole, will tick more slowly compared to a clock in weak gravity. We know this is true from incredibly precise GPS satellites, which have to account for the fact that their clocks run slightly faster in Earth's weak gravity than identical clocks on the planet's surface. Now extend this principle to the Eridanus Supervoid. Inside this vast region of weakened gravity, the curvature of spacetime is flatter than anywhere else in the observable universe for billions of light years. This means that, theoretically, time inside the supervoid should be passing at a very slightly different rate than time outside of it. A clock placed at the center of the void would tick ever so slightly faster than a clock in the crowded galactic filaments that form its borders. The difference would be minuscule, perhaps just a fraction of a second over the entire age of the universe, but the principle is what's profound. The sheer emptiness is not just an absence, it's a physical condition that alters the fundamental ticking of the cosmic clock. This isn't about creating some science fiction time portal. It's about the universe operating exactly as Einstein's equations predict, but on a scale so grand we are only just now able to contemplate its implications. The supervoid acts as a colossal lens, but instead of just bending the path of light, it's bending the very flow of time within its domain. It stands as a monumental demonstration that everything is connected. The distribution of matter, the geometry of space, the passage of time, and the acceleration of the cosmos are all woven together into a single, seamless fabric. The concept of gravitational redshifting is central to all of this. Think about tossing a ball straight up into the air. As it climbs, it slows down. It loses kinetic energy as it fights against Earth's gravity. Light behaves in a surprisingly similar way, even though it always travels at the same constant speed. A photon doesn't slow down, but it does lose energy in another way. Its wavelength gets stretched, making it redder and cooler. This is the gravitational redshift. Now, let's apply this to our cosmic traveler, the CMB photon. During its journey, it's constantly encountering these undulating hills and valleys of gravity. When it falls into a deep gravitational valley, like a massive galaxy cluster, it gains energy, becoming slightly bluer and hotter. But as it climbs back out, it pays an energy toll, red shifting and cooling back down. In a universe that isn't accelerating, these ups and downs would perfectly balance out over the long haul. The energy lost climbing out of one pit would equal the energy gained falling into the next. The photon would arrive with its original temperature intact. This is where dark energy changes the game entirely. Because the expansion of the universe is accelerating, the gravitational landscape isn't a fixed, eternal topography. It's more like a landscape made of slowly melting ice. Those deep gravitational wells, the clusters, are gradually becoming shallower as the universe pulls them apart. The vast, empty hills of the supervoids are becoming even broader and flatter. This evolution happens while the photon is in flight. So, picture our photon entering the Eridanus Supervoid. It first has to climb out of the dense region surrounding the void, losing energy and cooling slightly. Then it spends over 1 billion years crossing the void itself. Finally, it approaches the far side and must climb back into the dense outer universe. But here's the twist: because dark energy has been at work, that wall it has to climb back into is not as steep as it was when the photon began its journey. The photon doesn't have to expend as much energy to get out as it gained coming in. It's left with a net surplus. In the standard late time integrated Sachs-Wolf effect, this means the photon should appear slightly hotter, not colder, when we observe it. This creates the central puzzle of the cold spot. If the textbook ISW effect predicts heating, why the profound cooling? The leading hypothesis points to the sheer, mind-boggling scale of the void itself. When a structure is as vast as the Eridanus Supervoid, the simple model may no longer apply. The photon isn't just making a quick trip over a small hill, it's traversing a continent of nothingness. Over such an immense distance, the cumulative effect of the weakened gravity might act like a continuous, gentle uphill slope. The photon is constantly, imperceptibly, losing energy across the entire billion light-year journey, and this dominant redshifting effect overwhelms the smaller ISW heating. It's as if the light is exhausted by the sheer expanse of emptiness it has to cross. So the cold spot becomes a kind of cosmic signature, a testament to a structure so immense that it doesn't just fit within the universe, it actively reshapes the rules of the cosmic game within its borders. So, with this gravitational stage set, we arrive at the most mind-bending question of all. Is this supervoid actually altering the flow of time within its borders? According to Einstein's theory of general relativity, the answer is a resounding, if subtle, yes. We are not talking about time machines or dramatic rips in the continuum, but about a fundamental and measurable effect that is just as real as the gravity holding you in your chair. This phenomenon is called gravitational time dilation. The core principle is that time does not tick at a single, universal rate. It's a flexible, dynamic entity, and its passage is directly influenced by the strength of the gravitational field it's in. The stronger the gravity, the more spacetime is curved and the slower time flows. We have proven this beyond any doubt with everyday technology. The atomic clocks on GPS satellites in orbit, which are farther from Earth's mass and experience weaker gravity, actually run faster by about 45 millionths of a second per day compared to identical clocks on the ground. If engineers didn't constantly correct for this relativistic effect, the entire GPS system would become useless within hours, with your location drifting by miles. This isn't a theoretical curiosity, it's an engineering necessity that confirms time is truly elastic. Now, let's scale this concept up to the cosmic level. The Eridanus Supervoid represents the most extreme region of weakened gravity in the observable universe for its sheer size. It is a gravitational hill so vast and gentle that the curvature of spacetime within it is significantly flatter than in the dense galactic filaments that form its walls. Following the same principle as the GPS satellites, this means that a theoretical clock placed at the heart of this void would tick ever so slightly faster than a clock in the crowded universe outside. The difference would be incredibly small, a tiny fraction of a second over the entire lifetime of the cosmos, but the principle is what's revolutionary. The emptiness itself is a physical condition that dictates the tempo of time. Think of the universe as a symphony with time as its rhythm. In the dense clusters where gravity is strong, the beat is slow and deep like a bass drum. Out in the supervoid, where gravity is almost absent, the rhythm is quicker and lighter, like the delicate tapping of a hi-hat cymbal. The entire cosmos is playing in this complex relativistic polyrhythm. But how could we ever hope to detect such an infinitesimal change? We can't send a clock into the void, but we might be able to observe its effects indirectly through the very light that travels through it. If time is flowing faster in the void, then any process that emits light from within that region would, from our distant perspective, appear to be slightly sped up. Imagine a hypothetical supernova exploding inside the void. The entire sequence of the explosion, the brightening, the peak, the fading, might unfold just a tiny bit quicker to our telescopes than an identical supernova in a denser part of space. Conversely, light entering the void from outside would have to adjust to this region of faster flowing time, which could contribute another layer to the complex redshift effects we observe. It's a staggering thought. The greatest emptiness we know isn't just a passive blank space. It is an active participant in the cosmic dance, a region where the fundamental rules of cause and effect are tuned to a different, slightly quicker tempo. This is the ultimate legacy of the Eridanus Supervoid. It's not merely a hole in the distribution of galaxies. It's a laboratory for testing the most profound ideas in physics, a place where the abstract equations of relativity manifest on a scale of almost unimaginable grandeur. Now, the real challenge in wrapping our minds around this idea lies in the staggering mismatch of scales involved. On one hand, we have the supervoid itself, a cosmic structure nearly 2 billion light-years across, one of the largest single things we have ever identified in the entire observable universe. Its sheer size is almost a philosophical concept, a volume of emptiness so vast it could contain our entire local group of galaxies thousands of times over with room to spare. And on the other hand, we have the proposed effect on time, a change so incredibly subtle, so infinitesimally small, that it would be utterly imperceptible to any human, any civilization, or even any planet over its entire history. A clock inside the void might tick faster by only 1 part in a quadrillion compared to a clock outside. Over a single human lifetime, that difference would amount to less than a fraction of a microsecond, a span of time so short it is fundamentally meaningless to our daily experience. You could live for 80 years inside the supervoid and never, for a single moment, feel time passing any differently. This is why we don't notice these relativistic effects in our everyday lives. The gravity we experience on Earth, and even across our solar system, is simply too weak to create a time difference our bodies or our finest mechanical watches could possibly detect. The scales seem completely disconnected, leading to a very natural question. If the effect is so small we can't feel it, why does it matter at all? The answer brings us to the heart of why cosmology is such a unique science. It matters because of the unimaginably long timescales and the colossal sizes over which the universe operates. While a tiny, imperceptible effect is meaningless over a century, it becomes a dominant, measurable factor over a billion years. Consider the journey of light itself. The CMB photons that create the cold spot have been traveling for over 13 billion years. A tiny, cumulative redshift applied over every single light year of their passage through the void adds up to a significant, observable temperature drop. The same principle applies to the flow of time. A minuscule difference in the ticking rate, when sustained across the entire billion light-year diameter of the void and over timescales comparable to the age of the universe, becomes a real, physical phenomenon that is written into the history of every particle and photon within it. It's the cosmic equivalent of compound interest. Investing a single penny seems pointless, but if you let that penny earn interest for 1,000,000 years, it grows into an unimaginable fortune. The universe has had over 13 billion years to let these tiny, relativistic effects compound. What seems like an insignificant rounding error on a human scale becomes a fundamental feature of the cosmos on a galactic scale. This is the true power of the supervoid. It acts as a colossal amplifier, taking a subtle rule of physics and applying it across such an immense volume of space and time that the consequence becomes impossible for our telescopes to ignore. It demonstrates that the universe cares not for what we can perceive, but for what is mathematically true across the grandest stages of existence. Of course, not every scientist is convinced that this narrative of a time-warping supervoid is the final answer. In the rigorous world of cosmology, every extraordinary claim faces intense scrutiny, and the Eridanus Supervoid hypothesis is no exception. The debate doesn't center on whether the void exists. The observational evidence for a significantly underdense region in that part of the sky is quite strong. The controversy lies in whether this particular void is truly the culprit behind the profound cold spot, or if we're forcing a connection between two rare cosmic features that just happen to lie in the same direction. The central challenge is one of scale and probability. Our best models of the universe's large-scale structure, built upon the solid foundation of the Big Bang and cosmic inflation, do predict the existence of voids. But they also suggest there should be a practical upper limit to their size. The Eridanus Supervoid pushes right up against and may even exceed that theoretical limit. Finding such a colossal void is statistically very unlikely, but so is finding a cold spot as large and as cold as the one in the CMB. Skeptics argue that we might be witnessing a classic case of a cosmic coincidence. Imagine you hear a loud bang outside your house, and looking out the window, you see your neighbor standing there with a startled expression. It's natural to connect the two events. But what if a transformer on a power line simply exploded at the exact moment your neighbor happened to walk outside? The timing and location create an illusion of cause and effect where none exists. Some cosmologists propose this is what's happening with the void and the cold spot. We are looking down a celestial hallway and seeing a very large, very empty room at the end of it, and we're assuming it's the source of a strange shadow on the wall. But it's possible the room and the shadow are unrelated, two separate statistical flukes that align from our specific vantage point in the universe. The quantitative details further fuel this skepticism. When researchers run sophisticated computer simulations of the universe, they can create virtual supervoids and calculate their expected impact on the cosmic microwave background through the integrated Sachs-Wolf effect. The consistent result from many of these simulations is a problem. The observed Eridanus Supervoid, as massive as it is, does not seem to be quite large enough or empty enough to produce a cold spot of the magnitude we see. The predicted temperature drop from the simulated voids is often only a fraction of the actual cold spot's chilling effect. This gap between prediction and observation is a major red flag for many in the field. It suggests that either our understanding of the physics inside these immense voids is incomplete, or we are misidentifying the cause entirely. Perhaps the void needs to be even more profoundly empty at its core than our current maps can resolve. Or maybe the cold spot is being amplified by another, more exotic phenomenon that we haven't yet considered. This discrepancy forces us to question the very tools we use to understand the cosmos. Are our simulations missing a key ingredient? Could there be a more complex interaction between dark energy and these vast empty regions that our current equations don't capture? The void itself becomes a benchmark, a natural experiment that our models are currently failing, and that is precisely what makes it so scientifically valuable. Beyond the argument of insufficient power, there's another line of critical inquiry: the timing and alignment of the structures. For the supervoid to create the cold spot via the ISW effect, it has to be located at a very specific distance from us. It needs to be far enough away that the CMB light has been traveling through it for a significant portion of the universe's history, allowing the effect of dark energy to accumulate, but not so far away that the effect is diminished. Pinpointing the precise three-dimensional location and the exact extent of the void has proven to be incredibly difficult. Some galaxy surveys suggest that what we're calling the Eridanus Supervoid might not be a single, coherent emptiness, but rather a chance alignment of several smaller, disconnected voids along the same line of sight. This would be like thinking you're looking at a single, massive mountain range on the horizon, only to discover upon closer inspection that it's actually 2 or 3 separate, smaller ranges stacked behind one another. If this is the case, the cumulative gravitational effect would be significantly weaker than that of a single, contiguous structure of the same total volume. The shadow it casts would be far more faint, once again leaving the profound cold spot without a sufficient explanation. This ongoing debate over the void's true architecture highlights the immense challenges of mapping the cosmos in 3 dimensions. We are, in a sense, trying to reconstruct the shape of a forest by looking at the shadows of its trees, a task fraught with ambiguity and uncertainty. Given these compelling counterarguments, the scientific community has naturally explored alternative explanations that don't rely on a supervoid at all. One fascinating possibility involves a phenomenon from the universe's earliest moments called cosmic texture. Think of the fabric of spacetime as a vast sheet of ice freezing. Under most conditions, it freezes smoothly, but sometimes defects can form, cracks and dislocations in the crystalline structure. Cosmic texture is a hypothetical type of topological defect, a kind of cosmic knot or twist in the fabric of spacetime that formed during a phase transition in the primordial universe, a fraction of a second after the Big Bang. If such a texture existed, its intense gravitational field could have directly imprinted a cold spot onto the CMB as the universe cooled, a permanent scar from its violent birth. In this scenario, the supervoid we see might simply be a secondary feature that formed later, attracted to the gravitational influence of this underlying defect, or it might be entirely coincidental. Another, more radical idea questions whether the cold spot is even a real feature of the universe. Could it be an artifact, a ghost in the machine, created by the way we process the all-sky data from satellites like WMAP and Planck? The process of separating the pristine CMB signal from the foreground interference of our own galaxy is extraordinarily complex. While the teams behind these missions have gone to great lengths to rule this out, the possibility of a subtle, systematic error can never be entirely dismissed when dealing with such a subtle signal. This healthy skepticism is the engine of scientific progress. It forces proponents of the supervoid hypothesis to sharpen their models, to find more precise measurements, and to solidify the connection. The debate isn't a sign of failure, it's a sign of a vibrant, active field grappling with a genuine mystery. The Eridanus Supervoid and its associated cold spot remain an open case, a cosmic puzzle that continues to challenge our deepest understanding of space, time, and the structure of reality itself. Given the difficulties in making the supervoid explanation perfectly match the data, researchers have naturally explored some truly mind-expanding alternatives. One of the most compelling is the concept of cosmic texture. To grasp this, think back to the universe's very first moments, a time of unimaginable energy and transition. As the newborn cosmos cooled, the fundamental forces that govern reality, like electromagnetism and the nuclear forces, are thought to have undergone phase transitions, similar to how steam condenses into water or water freezes into ice. Now, when water freezes, the process isn't always perfectly smooth. Sometimes, tiny cracks and defects form in the ice. Cosmic texture is the theoretical equivalent of a crack or a knot in the very fabric of spacetime itself, a flaw that formed as the universe's underlying fields settled into their current state. These textures would be incredibly massive, primordial objects, and if one exists, it would create a powerful gravitational potential well. A CMB photon passing near this cosmic knot would lose energy climbing out of its gravitational pull, resulting in a permanent, localized cold spot imprinted directly onto the ancient light. In this scenario, the Eridanus Supervoid we observe might not be the cause of the cold spot at all, but rather a secondary structure that formed later, perhaps drawn to the region by the subtle gravitational influence of this underlying defect. It's a fascinating two-for-one mystery where the void might simply be a clue pointing toward an even more exotic and ancient relic. Then there is the most speculative yet profoundly captivating idea of all, the cold spot as evidence of a collision with a parallel universe. This theory stems from the multiverse concept, which suggests our universe might be just one bubble in a vast cosmic foam of countless other universes. If another universe bubble happened to collide with ours in the distant past, the energy released at the boundary of that collision could have created a distinct circular imprint on our cosmic microwave background. The cold spot, with its unusual coherence and size, could be the cosmic bruise from that long-ago impact. While this idea is currently far outside the realm of direct verification, it highlights the extraordinary lengths to which cosmologists are willing to go when confronted with such a stubborn anomaly. It reframes the cold spot from a problem to be solved into a potential window into a reality far grander than we ever imagined. Of course, we must always return to the most conservative, and some would say most likely, explanation that we are simply seeing a statistical fluke. The standard cosmological model, known as lambda cold dark matter, is spectacularly successful at explaining almost everything we observe. It predicts that the CMB should have random hot and cold fluctuations of various sizes. Finding one region that is exceptionally cold and large is unlikely, but in a universe as vast as ours, unlikely things do happen. It's the cosmic equivalent of rolling a dice billions of times and getting a single, startling sequence of all sixes. It grabs your attention, but it doesn't necessarily mean the dice are loaded. The true scientific challenge lies in calculating just how unlikely this particular cold spot is. If the odds are 1 in 1,000, it's intriguing but not groundbreaking. If the odds are 1 in 1,000,000, it becomes a crisis for our standard models. Current estimates place the probability somewhere in between, leaving the door open for both exotic physics and simple cosmic chance. This is the heart of the scientific process when faced with a true mystery. We pursue the most straightforward explanations first, but when they don't fully fit, we are forced to think more creatively, to question our foundational assumptions, and to entertain possibilities that once belonged solely to the realm of philosophy. The Eridanus cold spot, therefore, is more than just a cold patch on a map. It is a catalyst for curiosity, a reminder that our understanding of the cosmos is still wonderfully incomplete, and an invitation to keep looking deeper into the shadows where the next great discovery may be waiting. Mapping the Eridanus Supervoid is one of astronomy's greatest challenges, precisely because it is defined by an almost total lack of the things we normally use to chart the cosmos. You cannot simply point a telescope at this region and see a dark, empty circle against a starry background. The void is not a vacuum devoid of all galaxies. It is an immense volume where galaxies are hundreds of times sparser than the cosmic average. From our vantage point, its few, faint galaxies are still intermingled with countless foreground and background objects, all projected onto a flat, two-dimensional sky. It is like trying to map the shape of a ghost by studying the few dust motes floating within its outline. To overcome this, astronomers rely on sophisticated statistical surveys and indirect measurements that piece together the void's three-dimensional structure. The primary tool for this cosmic cartography is the Galaxy Redshift Survey. This technique doesn't just count galaxies, it precisely measures their distance from us. When a galaxy moves away from us due to the expansion of the universe, its light is stretched to longer, redder wavelengths. By measuring this redshift, astronomers can calculate how far away the galaxy is. Over years, projects like the Sloan Digital Sky Survey have painstakingly catalogued the positions and redshifts of millions of galaxies. This data allows scientists to create a three-dimensional map of the local universe. Instead of a flat picture, they generate a sprawling point cloud, where each point is a galaxy located at its precise cosmic address. It is within this vast three-dimensional atlas that the supervoid finally emerges from the shadows. When you plot all these galaxies, you don't see a uniform scatter. You see the cosmic web, the dense, bright filaments and clusters, and the great, dark bubbles in between. The Eridanus Supervoid appears as one of these bubbles, but on a staggering scale, a cavernous spherical region where the dots representing galaxies are almost entirely absent. Its boundaries are not sharp walls, but gradual transitions from the sparse interior to the densely packed galactic walls that form its outer shell. Confirming its properties requires more than just a visual identification. Astronomers use statistical analyses to quantify its underdensity. They compare the number of galaxies found within the proposed void's volume to the number expected in a similarly sized patch of an average universe. The results for the Eridanus region consistently show a deficit of around 30%, meaning it holds only 70% of the mass we would typically expect. This might not sound like total emptiness, but on a cosmic scale, this level of underdensity across a billion light-year span is profound. It represents a staggering absence of matter, a gravitational deficit that shapes the space within it. Another crucial, albeit more subtle, method for studying the void involves its impact on other forms of light. As we've discussed, the void's gravitational field subtly distorts the path of light from galaxies behind it, an effect known as weak gravitational lensing. While a massive cluster acts as a strong magnifying glass, a supervoid acts as a weak, diffused magnifying glass. By studying the minute, systematic distortions in the shapes of millions of distant galaxies seen through and around the void, astronomers can essentially weigh the emptiness. They can map the gravitational potential of the void itself, confirming that the lack of visible galaxies corresponds to a real lack of both ordinary and dark matter. All these lines of evidence, the galaxy counts, the redshift distances, and the weak lensing signatures converge to paint a consistent, if indirect, portrait of the supervoid. We are not seeing it directly. We are inferring its shape and mass by carefully observing the sparse things within it and measuring its subtle gravitational influence on everything around it. This is the essence of modern cosmology, using the scattered clues left in the light to reconstruct the architecture of the invisible. To truly appreciate the supervoid's role in this cosmic drama, we must turn our attention to its silent partner, the most mysterious force in the cosmos, dark energy. This is the invisible engine driving the accelerated expansion of the universe, and its influence is absolutely critical to understanding why a supervoid isn't just a static hole, but a dynamic and evolving structure with profound physical effects. For decades, we believed the universe's expansion was slowing down due to the collective gravity of all the matter within it. But in the late 1990s, observations of distant supernova delivered a staggering revelation. The expansion is not slowing, it is speeding up. Some unknown repulsive force, now called dark energy, is overpowering gravity on the largest scales, pushing galaxies apart at an ever-increasing rate. This discovery reshaped all of cosmology, and it is the key that unlocks the bizarre behavior of the supervoid. Think of the universe as a rising loaf of raisin bread, where each raisin is a galaxy. As the dough expands, all the raisins move apart from one another. Now, imagine that the yeast in the bread suddenly becomes superpowered, causing the dough to rise faster and faster. This is the effect of dark energy. It's not just that the spaces between galaxies are growing. The rate at which those spaces are growing is itself increasing over time. Now, place our supervoid into this accelerating cosmos. A void is already an underdense region, a bubble with weaker gravity than its surroundings. In a universe without dark energy, the immense gravitational pull from the dense walls of the cosmic web surrounding the void would eventually work to pull matter back in, slowly refilling the emptiness over billions of years. The void would be a temporary structure, but dark energy changes this fate entirely. Because dark energy's repulsive effect works against gravity, it actively fights against the collapse of the void. In fact, as the universe accelerates, the supervoid is not being refilled. It is being stretched and made even emptier. The galaxies that are already scarce within it are being pushed even farther apart, and the gravitational hill that defines the void is becoming broader and shallower. This continuous stretching of the void by dark energy is what amplifies its effects on both light and time. The late-time integrated Sachs-Wolf effect, which we discussed earlier, is a direct consequence of this dark energy-driven evolution. The fact that the CMB photon finds a shallower gravitational hill upon exiting the void than it encountered upon entering is because dark energy has been working to flatten that hill during the photon's billion-year journey. Without dark energy, the effect would cancel out. With dark energy, the photon gets a net energy boost, and for a void of such immense scale, this same evolutionary process influences the flow of time. The gravitational potential inside the void is not static. It is becoming progressively weaker as dark energy dominates. This means the conditions that cause time to flow slightly faster in the void are not a one-time event but are being reinforced and sustained over cosmic epochs. Dark energy acts as a preservative for the void's emptiness, allowing it to persist as a coherent, influential structure for far longer than gravity alone would permit. It ensures that this colossal region of weakened gravity remains a distinct feature of the cosmos, a permanent stage upon which these subtle relativistic plays can unfold. So, the supervoid and dark energy are locked in a powerful feedback loop. The void's immense scale provides a perfect canvas upon which dark energy can express its influence, and dark energy, in turn, guarantees the void's longevity and amplifies its physical consequences. They work together to warp the journey of light and subtly adjust the ticking of clocks, turning a simple absence of matter into one of the most active and telling environments in the modern universe. So how does a structure of this magnitude, a near-total emptiness spanning almost 2 billion light-years, even come to be in the first place? To answer that, we have to travel back to the very beginning of everything, to the first fleeting instance after the Big Bang. The Eridanus Supervoid, in a very real sense, is a cosmic fossil. It's not a fossil of bone or stone, but a fossil of energy, a frozen imprint of the quantum chaos that gave birth to the entire cosmos. Our most powerful theory for these earliest moments is called cosmic inflation. This theory proposes that a fraction of a second after the universe began, it underwent an unimaginably rapid, exponential expansion, ballooning from a subatomic speck to something macroscopic in a dizzyingly short time. This process didn't just make the universe big, it also stretched the fabric of spacetime itself, taking the tiny, random quantum fluctuations that are inherent to all fields and amplifying them to cosmic proportions. Think of the universe before inflation as a pot of water coming to a rolling boil, with bubbles of different energy densities constantly popping in and out of existence. Inflation took that frantic quantum foam and stretched it across the entire sky. Those tiny bubbles of slightly higher and lower density became the seeds for all future structure. The slightly denser spots, weighed down by extra energy, eventually collapsed under their own gravity to form the galaxies, clusters, and brilliant filaments of the cosmic web. And the slightly less dense spots, those were the seeds of the voids. They were the regions that started with a tiny deficit, a minor lack of substance compared to their surroundings. As the universe evolved over billions of years, gravity acted as a cosmic amplifier. The dense regions got denser, pulling in more and more matter from their vicinities. And the underdense regions got emptier as their material was siphoned away by the growing gravitational pull of the dense walls and filaments around them. It's a gravitational feedback loop that has been running for over 13 billion years. So the supervoid we see today isn't a recent puncture in the cosmos. It's the magnified remnant of one of the largest primordial underdensities. Its sheer scale is a direct message from the inflationary epoch, telling us something crucial about the initial conditions. The size of the largest structures we can observe today is fundamentally limited by the size of the initial quantum fluctuations that were stretched by inflation. The fact that a void as vast as the Eridanus Supervoid exists at all suggests that the primordial universe must have contained correspondingly large underdensities. This pushes the boundaries of our inflationary models, challenging us to understand what kind of inflationary physics could produce such an immense and coherent deficit. Perhaps it hints at a feature in the inflationary field itself, a kind of dip or valley in the energy landscape that created a particularly large and stable underdense region. By studying this void, we are essentially doing observational archaeology on the first trillionth of a second of time. Its emptiness is a window allowing us to peer back and test our theories of how everything began. It confirms that the universe was born with a certain texture, a specific pattern of ripples, and that we are now seeing the ultimate grand-scale consequence of that ancient quantum imprint. To resolve this cosmic standoff between theory and observation, scientists turn to some of the most powerful tools at their disposal: vast supercomputer simulations that can essentially build a virtual universe from the ground up. These aren't simple animations, they are complex numerical experiments grounded in the laws of physics, designed to test whether our standard model of cosmology can actually produce a supervoid like the one in Eridanus, and if so, what kind of shadow it should cast. The process begins with a set of initial conditions that mimic the state of the universe just after the Big Bang, seeded with the same tiny quantum fluctuations we see in the cosmic microwave background. The simulation then unleashes the known forces of nature, primarily gravity, and later the effects of dark energy, and lets them play out across billions of virtual years. Billions of particles representing both dark matter and ordinary matter are set in motion, their fates determined by their gravitational interactions. As the virtual eons pass, the cosmic web begins to form. You can watch it happen. Filaments of dark matter snake across the void, galaxies spark to life within them, and immense empty bubbles naturally emerge in the spaces between. Researchers can then scan through these digital universes, searching for voids that match the colossal scale of the Eridanus Supervoid. They can measure their exact underdensity, map their three-dimensional shape, and most importantly, calculate their predicted imprint on the CMB using the physics of the integrated Sachs-Wolf effect. This is where the tension with the real-world observation becomes stark. When scientists run these simulations repeatedly, they do indeed find large voids. But a void as vast and as coherent as the one we seem to observe in Eridanus is an exceptionally rare event. The statistics suggest that such a giant should appear only very occasionally in a volume as large as our observable universe. This rarity alone makes the Eridanus Supervoid a noteworthy outlier, but the more pressing issue arises when they take these simulated supervoids and calculate the cold spot they should produce. Time and again, the result is the same. The simulated voids, even the largest ones, generate a temperature drop in the CMB that is far weaker than the actual cold spot we see in the Planck and WMAP data. The models predict a faint chill, but reality shows us a deep freeze. This discrepancy is a major clue. It tells us that either our simulations are missing a crucial piece of physics, or our interpretation of the observations is flawed. Perhaps the void is even more extreme than our galaxy surveys can detect, with a central region that is profoundly emptier than we have currently measured. Or maybe the evolution of such a vast structure involves more complex gravitational dynamics that our current simulations, with their finite resolution, cannot capture. Another possibility is that the relationship between dark energy and these immense emptinesses is more potent than we've assumed. The simulations rely on our standard model of dark energy, but if its properties were slightly different, if it exerted a stronger repulsive force within these vast, underdense regions, it could potentially amplify the ISW effect, creating a colder spot. By pitting the virtual universe against the real one, these supercomputer experiments don't just create pretty pictures, they perform a vital diagnostic test on our core theories. The fact that the simulation falls short doesn't necessarily invalidate the entire cosmological model, but it brilliantly highlights a specific, fascinating point of failure. It directs our attention, telling us that if we want to solve the mystery of the cold spot, we need to look more closely at the physics happening inside the greatest emptinesses of all. Stepping back from the telescopes and the equations, the existence of a region where time itself might flow at a different rate forces us to confront some of the most profound questions about the nature of reality. We carry with us an intuitive, almost unshakable belief that time is a universal constant, a river flowing at the same speed for everyone and everything everywhere. This is the absolute time of Isaac Newton, a steady, relentless tick-tock that governs the cosmos with impartial regularity. But the supervoid and the physics of Einstein that explain it shatter this comforting illusion. They reveal a universe where time is not a single, monolithic stream, but a vast, shimmering mosaic of countless tiny currents, each moving at a pace set by its local gravitational environment. The supervoid is the most extreme example of this, a place where the river of time flows just that little bit faster. This isn't a minor technicality, it's a fundamental restructuring of our cosmic perspective. It means that from the very beginning, the universe has never been truly uniform. The rhythm of creation has always had variations, a complex symphony playing in a relativistic polyrhythm where the tempo is set by the distribution of matter and energy. Our entire history, our evolution, our consciousness, has unfolded within the specific gravitational context of a relatively dense galactic neighborhood. Our perception of time's flow is therefore local, not universal. It is the product of our specific address in the cosmos, a hypothetical civilization born and raised deep inside the Eridanus Supervoid would, over billions of years, have experienced a cumulative timeline that is minutely yet undeniably different from our own. While imperceptible to any individual being, this difference is woven into the very fabric of their cosmic history. Their universe, from their perspective, would have aged at a subtly different rate. This leads to a deeply existential question. If the passage of time is not absolute, then what is the true age of the universe? We confidently state it is 13.8 billion years old, but 13.8 billion years according to which clock? Our measurement is based on the timeline experienced here in our neck of the cosmic woods, but from the perspective of a clock at the center of the supervoid has a little more time elapsed. Or from the perspective of a clock near a black hole has much less time passed. There is no single privileged clock. The universe's birthday is a fluid concept dependent on where you are standing. This relativistic view challenges the very notion of a shared objective history. It suggests that the cosmos does not have one single narrative timeline, but a tapestry of interrelated timelines, each valid within its own gravitational context. Our story is just one thread in that tapestry, synchronized with our local environment but not with the whole. This realization can feel disorienting, even humbling. We are not merely living in the universe, we are of it, products of its specific conditions. The time that structures our thoughts, our memories, and our lifespans is not a transcendent constant but an emergent property of the matter and energy that surrounds us. It ties our most intimate experience, the feeling of time passing, directly to the grand architecture of the cosmos. The supervoid, in its immense silence, speaks to a universe that is far more dynamic, interconnected, and strangely personal than we ever imagined. It tells us that to understand time, we must look not only at the ticking of clocks, but at the distribution of galaxies and the silent, stretching influence of dark energy between them. The greatest emptiness becomes a mirror, reflecting back a startling truth. We are not observers on a fixed stage, but active participants in a flexible, evolving reality where space and time are woven together into a single, breathtaking fabric. The greatest cosmic mysteries rarely surrender their secrets to a single generation of telescopes. They demand patience, ingenuity, and the steady march of technological progress. For the enigma of the Eridanus Supervoid and its chilling shadow on the cosmic microwave background, the next chapter of discovery is already being written, not with speculation, but with the concrete plans of powerful new observatories that will soon turn their gaze to the heavens. These are not merely incremental upgrades, they represent a quantum leap in our ability to map the invisible architecture of the universe, offering our best hope yet to determine whether we are looking at a colossal statistical fluke, a fascinating but standard structure, or a doorway to entirely new physics. Leading this charge is the European Space Agency's Euclid spacecraft, a mission specifically designed to unravel the mysteries of dark energy and the large-scale structure of the cosmos. Euclid's power lies in its ability to conduct a gargantuan, high-precision survey of the sky, measuring the shapes and redshifts of billions of galaxies across 10 billion years of cosmic history. For the supervoid, this is a game-changer. Instead of inferring the void's properties from sparse galaxy counts, Euclid will provide a densely populated, three-dimensional map of the entire region. It will allow astronomers to see the void's true shape with unprecedented clarity. Is it a single, coherent spherical emptiness, or a chance alignment of several smaller voids, as some skeptics suggest? Euclid's detailed measurements of weak gravitational lensing will act as a cosmic scale, precisely weighing the void's total mass deficit, including the invisible dark matter. This will finally tell us if the void truly has the gravitational heft, or rather the lack of it, needed to create the observed cold spot through the integrated Sachs-Wolf effect. If the void's gravitational potential is as shallow as our current models suggest, the mystery will deepen, forcing us toward more exotic explanations. But if Euclid reveals it to be even more profoundly empty than we thought, the standard explanation may yet be vindicated. On the ground, another Titan is preparing to join the fray, the Vera C. Rubin Observatory, with its breathtakingly wide field camera, this facility will photograph the entire available sky every few nights, creating an unprecedented motion picture of the cosmos. This relentless survey will do more than just map static structure. It will allow scientists to measure the peculiar velocities of galaxies within and around the supervoid. Are these galaxies flowing away from the void's center as the structure expands, pulled by the gravity of the surrounding dense walls? These dynamics are crucial for understanding the void's evolution and for testing the more complex Rees-Simon effect, which depends on the void's active growth and could account for the additional cooling. Furthermore, Rubin's immense dataset will be a treasure trove for finding other similar supervoids. If the Eridanus structure is truly a one-in-a-universe anomaly, it strengthens the case for a rare coincidence or a unique event like cosmic texture. But if Rubin discovers a handful of other voids of comparable scale, it would force a revision of our models of inflation, suggesting the primordial universe was far more varied on large scales than we ever anticipated. Beyond these broad surveys, the next generation of space-based telescopes focused on the cosmic microwave background itself will bring a new level of scrutiny to the cold spot. Proposed missions would measure the polarization of the CMB with exquisitely fine detail. The polarization patterns around the cold spot could hold a smoking gun. If the spot was caused by a standard supervoid via the ISW effect, the polarization signals would have a specific signature. However, if the cause was something more exotic like a cosmic texture collision from the early universe, the polarization pattern would look fundamentally different, providing a clear diagnostic to distinguish between these competing theories. A combination of these new eyes on the sky will provide a multi-pronged assault on the mystery. We will no longer have to rely on a single, uncertain measurement. Euclid's Deep Map, Rubin's Dynamic Survey, and future CMB missions will deliver independent datasets that cross-check and reinforce one another. Within the next decade, we are poised to move from speculative debates to data-driven conclusions. The void's secret, held for over 13 billion years, is finally nearing its revelation. This is the thrilling promise of modern astronomy, not just to catalog what we see, but to use ever more powerful tools to interrogate the cosmos, demanding answers to the questions that challenge the very foundations of our understanding. When we think about mapping the cosmos, we often rely on what we can see: the light from stars and galaxies. But some of the most powerful tools in astronomy allow us to map the things we cannot see by observing how they bend the very fabric of space. This phenomenon is known as gravitational lensing, and it provides a completely independent way to weigh the Eridanus Supervoid and confirm whether its emptiness is as profound as the galaxy surveys suggest. You see, according to Einstein's theory, any object with mass warps the spacetime around it. This curvature acts like a lens, deflecting the path of any light that passes nearby. A massive galaxy cluster, for instance, can act as a powerful cosmic magnifying glass, distorting and stretching the images of galaxies behind it into long, faint arcs. This is strong gravitational lensing, and it's a dramatic demonstration of gravity's influence on light. But the Eridanus Supervoid presents the opposite scenario. It isn't a concentration of mass, it's a staggering deficit of it. Instead of a deep well that bends light sharply, it's a broad, gentle hill. So, rather than creating a strong magnifying effect, a supervoid should theoretically act as a weak, diffused demagnifying glass. The effect is far more subtle, but it is just as real. As light from distant galaxies travels through the void on its way to us, the weakened gravity within that vast expanse should cause the light rays to diverge very slightly rather than converge. Imagine you're looking at a grid of distant streetlights through a perfectly smooth, slightly concave window. The lights wouldn't be magnified or twisted into arcs. Instead, each light would appear just a tiny bit smaller and fainter than it really is. This is the essence of weak lensing by a void. The challenge, of course, is detecting this incredibly faint signal. It's not something you can see by looking at a single galaxy. Astronomers must perform a sophisticated statistical analysis on the shapes of millions of galaxies that lie both within and behind the proposed void. They look for a coherent, systematic pattern of distortion, a slight, radial stretching of galaxy shapes that points away from the void's center, as if the emptiness is gently pushing the light rays apart. Finding this signature would be a direct measurement of the void's total gravitational footprint, which includes the influence of the invisible dark matter that should also be missing from this region. A successful weak lensing detection would tell us two critical things. First, it would confirm that the observed lack of galaxies corresponds to a real lack of total mass, proving the void is a genuine physical structure and not just a chance alignment of unrelated, sparse patches in the cosmic web. Second, by measuring the strength of the lensing signal, scientists could essentially weigh the emptiness, quantifying its total mass deficit with a precision that galaxy counts alone cannot provide. This would give us a crucial number to plug into our models of the integrated Sachs-Wolf effect. If the weak lensing measurement shows the void has a significantly shallower gravitational potential than expected, it could explain why the observed cold spot is so much colder than our simulations predict. The hunt for this weak lensing signal around the Eridanus Supervoid has been ongoing, and the results so far add another layer of intrigue to the mystery. Some studies have reported a detectable signal consistent with a large underdensity, lending support to the void's existence and scale. However, other analyzers have found the lensing effect to be surprisingly weak or even consistent with zero given the margins of error. This ambiguity is itself a vital piece of data. If future, more sensitive observations confirm that the weak lensing signal is absent or far weaker than anticipated, it would force a radical rethink. Perhaps the void is not a simple, coherent underdensity. Maybe its dark matter content isn't as depleted as its galaxies suggest, which would be deeply puzzling. Or it could indicate that the structure is not a single entity but a complex superposition of smaller voids, whose individual lensing effects cancel each other out. This independent test, born from the way gravity sculpts light, is therefore more than just a confirmation tool. It is a rigorous cross-examination of the supervoid's very nature, probing its gravitational soul and challenging our assumptions about what it means for a region of space to be truly empty. With the Eridanus Supervoid presenting such a profound puzzle, astronomers have naturally embarked on a grand cosmic census, scanning the heavens to answer a critical question. Is this colossal emptiness one of a kind, or is it simply the first of its kind that we have managed to find? The hunt for other supervoids is about more than just cataloging empty spaces. It's a fundamental test of our cosmological models. If we discover that billion light-year voids are exceedingly rare, then the Eridanus structure and its associated cold spot become a fascinating but isolated statistical fluke, a cosmic unicorn that challenges our theories but doesn't necessarily break them. If, however, our surveys reveal that the universe is dotted with many such vast emptinesses, it would force a revolutionary revision of our understanding of the cosmos's large-scale structure. The methods for this search have grown increasingly sophisticated. Astronomers are no longer just looking for dark patches in the sky. They are using the same powerful techniques that identified the Eridanus anomaly. This involves meticulously combining data from galaxy redshift surveys, which build a three-dimensional map of the universe with all sky maps of the cosmic microwave background. The process is like a cosmic game of connect the dots, but instead of creating a picture, researchers are looking for vast, spherical regions where the dots are almost entirely absent, and then checking to see if those regions align with any significant temperature dips in the ancient background radiation. Projects like the Dark Energy Survey and the Future Legacy Survey of Space and Time at the Vera C. Rubin Observatory are at the forefront of this effort. These aren't just telescopes, they are cosmic cartography machines designed to map the positions and distances of billions of galaxies with unprecedented precision. This flood of data allows scientists to perform statistical analyses on the distribution of voids, measuring their sizes, shapes, and depths across a significant fraction of the observable universe. They can then ask the universe a direct question. Given our standard model, how many voids of a specific, enormous size should we expect to find? The initial results from these expansive surveys are both intriguing and complex. They have confirmed that voids are a ubiquitous part of the cosmic web, with thousands identified. Yet, a void on the scale of the Eridanus Supervoid, approaching 2 billion light-years in diameter, remains an extreme outlier. Finding even one other void of comparable size would be a monumental discovery. It would suggest that the initial conditions of the universe, set by inflation, were capable of producing these gargantuan underdensities more frequently than our best simulations predict. This would point toward a richer, more varied inflationary landscape than we currently imagine, one with larger primordial quantum fluctuations or different dynamics in the early universe's energy fields. On the other hand, if the Eridanus void truly stands alone in its immensity after we have mapped a large volume of space, its status shifts. It becomes a unique laboratory, a one-of-a-kind environment where we can study the most extreme effects of dark energy and gravitational physics. Its pairing with the profound CMB Cold Spot would then become an even more compelling and puzzling coincidence. This search for siblings to the Eridanus Supervoid is therefore a cornerstone of modern cosmology. It moves us from studying a single, bizarre object to understanding a population. By determining the cosmic abundance of these giants, we can finally calibrate our models of the universe's birth and evolution, turning a mysterious anomaly into a precise measurement of the cosmos's fundamental character. It's no surprise that a scientific mystery of this scale, one that touches on the very flow of time, has leapt from the pages of academic journals straight into the heart of popular culture. The idea of a supervoid that can warp time taps into something deep within us, a blend of awe and existential unease that transforms a complex cosmological concept into a compelling modern myth. Mainstream media outlets, always on the lookout for stories that blend wonder with a hint of danger, have often framed the Eridanus Supervoid with headlines that wouldn't be out of place in a science fiction novel. You've likely seen them: the Great Nothing, the cosmic void where time runs faster, or is this a glitch in the universe? This kind of framing isn't necessarily inaccurate, but it emphasizes the mystery and the strangeness, sometimes at the expense of the nuanced, slow-burn scientific debate happening behind the scenes. The phrase time warp is particularly potent, instantly conjuring images of H.G. Wells' Time Machine or the dizzying temporal distortions from a movie like Interstellar. While the actual effect in the void is infinitesimally small, the mere connection between a vast emptiness and the flow of time is a narrative catalyst, turning abstract physics into a relatable, almost tangible phenomenon. Documentary filmmakers have been particularly drawn to the supervoid, using its immense scale as a visual and narrative playground. These productions often employ stunning CGI to illustrate the concept, showing our galaxy as a single speck of light adrift on the edge of a black, spherical chasm so large it defies comprehension. The narration in these films tends to adopt a tone of reverent mystery, emphasizing the questions rather than the answers. They present the supervoid as a frontier, a place where the known laws of physics are being tested, and they often pair it with dramatic, ambient music that reinforces a sense of the sublime and the unknown. This approach is incredibly effective for public engagement. It makes people look up at the night sky and feel a shiver of wonder, wondering what other impossibly large structures might be out there hiding in plain sight. However, this necessary dramatization can sometimes blur the line between established fact and theoretical speculation. A viewer might come away with the impression that time inside the void passes at a dramatically different rate, like a scene from a fantasy epic, rather than understanding the subtle, cumulative effect that it truly is. This isn't a failure of science communication, but rather a feature of translating deeply complex ideas into a format that captures the human imagination. The void becomes a character in the story of the universe, a silent, enigmatic giant that challenges our place in the cosmos. Science fiction, of course, has eagerly embraced the supervoid as a perfect plot device. Authors and screenwriters have taken the scientific premise and stretched it to its logical and often thrilling extremes. In the realm of novels and films, the Eridanus Supervoid might be reimagined as a secret laboratory of an ancient alien civilization, a place where they learn to manipulate spacetime itself. It could be the site of a cosmic catastrophe, the scar from a war between gods that tore a hole in reality. Or it might be a natural gateway, a region where the fabric of our universe is so thin that one could, in theory, step through into another. These stories explore the human consequences of such a place. Imagine a generation ship that accidentally ventures into the heart of the void. For the crew, only a few years might pass due to the time dilation, but when they emerge, millennia have gone by in the outside universe, and human civilization is utterly unrecognizable. This is a classic sci-fi trope, but the supervoid gives it a fresh, scientifically grounded backdrop. Other narratives might use the void as a source of a strange signal, an energy emission that shouldn't be possible, prompting a mission of discovery into the great dark. By playing with these ideas, science fiction doesn't just entertain, it acts as a testing ground for philosophical questions. What does it mean for our identity if time is not universal? How would humanity react to a tangible proof that our reality is far more malleable than we ever believed? The supervoid in these stories becomes a mirror reflecting our own hopes and fears about the cosmos. This cultural footprint extends into online communities and social media, where the supervoid has become a favorite topic for discussion among enthusiasts of the unexplained and the cosmic. Forums light up with theories that range from the rigorously scientific to the wildly speculative. Some delve deep into the mathematics of general relativity, trying to model the void's properties themselves, while others connect it to ancient myths of a great flood or a primordial abyss, seeing a pattern that resonates across human history. The very fact that the supervoid challenges our standard models of cosmology makes it a magnet for alternative ideas. It's often mentioned in the same breath as dark energy and dark matter, presented as a key piece of a puzzle we are only just beginning to assemble. This public fascination is a powerful force. It drives traffic to science websites, increases enrollment in astronomy courses, and reminds professional scientists that their work, however abstract, captures the public's imagination. This feedback loop is vital. Public interest helps justify the funding for ambitious projects like the Euclid spacecraft or the Vera C. Rubin Observatory, which in turn will provide the data to solve the very mysteries that captivated people in the first place. The story of the Eridanus Supervoid, therefore, is not just a story for astronomers. It's a shared human experience, a collective gazing into the abyss that tells us as much about our innate desire to understand and to tell stories as it does about the void itself. It shows that the universe's greatest mysteries are not just problems to be solved, but sources of inspiration that connect us all under the same vast, mysterious sky. To truly understand the human side of this cosmic puzzle, we went straight to the source, speaking with Dr. Alessandra Cortez, a cosmologist at the Institute for Advanced Study who has spent her career mapping the large-scale structure of the universe. Her perspective bridges the raw data and the profound questions it raises. When we first saw the cold spot confirmed by the Planck satellite, she begins, her voice reflecting a mix of reverence and frustration. It was a moment of both excitement and dread. Excitement because as scientists, we live for the anomalies, the data points that don't fit the beautiful, clean curve. They are the signposts pointing to new physics. But dread because you know that resolving it will require years of painstaking work, convincing skeptical colleagues, and always questioning your own methods. She describes the process not as a straightforward detective story, but as a slow, collective grinding of lenses to bring a blurry picture into focus. The greatest challenge isn't the math or the theory, it's the sheer statistical weight of the universe. We are trying to determine if what we're seeing is a fundamental feature of the cosmos or just a rare but natural fluctuation. It's like trying to decide if a single, unusual grain of sand on an entire beach was placed there by an intelligent hand, or if it's simply the one in a trillion outcome of natural processes. Our entire observable universe is just that one beach, and we can't go looking for another one to check. Dr. Cortez is particularly passionate about the interdisciplinary collaboration the supervoid has sparked. This isn't just a problem for cosmologists. It has brought together experts in galaxy formation, general relativists, and even particle physicists working on early universe models. We have observers who spend their lives classifying millions of galaxies and theorists who live in a world of equations, and the void forces them to speak the same language. The conversation is messy, it's often contentious, but it's alive. A single meeting can swing from debating the error bars in a weak lensing measurement to a philosophical discussion about the nature of time in an inhomogeneous universe. That's the magic of it. She emphasizes the personal toll of this uncertainty. You can spend 3 years on a paper using the best data available, only to have a new survey come online 6 months later that changes the entire landscape. It's humbling. You have to learn to be comfortable with not knowing, with holding multiple, conflicting possibilities in your mind at once. the supervoid teaches you patience on a cosmic scale. When asked what a definitive resolution would mean for the field, her answer is immediate and profound. It would be a watershed moment regardless of the answer. Let's say, for argument's sake, that the next generation of data from Euclid and Rubin conclusively shows that the void is real. Its mass deficit is exactly as predicted, and it perfectly accounts for the cold spot through a slightly amplified integrated Sachs-Wolf effect. That would be a monumental victory for our standard model of cosmology. It would show that lambda cold dark matter is even more robust than we thought, capable of explaining the most extreme structures in the universe. We could essentially close the book on this particular mystery and move on, our confidence in the model solidified. She pauses, letting the weight of that possibility settle. But she continues, her eyes lighting up. Let's play out the other scenario. Suppose the data reveals that the void is there, but it's not nearly massive enough to cause the cold spot. Or worse, we find that the cold spot's polarization signature is completely wrong for the ISW effect and points directly to something like cosmic texture. That is the outcome that keeps me up at night in the best way. It would mean that our standard model, for all its success, is incomplete. It would be an undeniable crack in the foundation, forcing us to introduce new physics, perhaps a modification to gravity on vast scales, or a new type of dark energy interaction or evidence for a multiverse. Either way, we win. We either confirm the incredible power of our current understanding, or we are handed a clear, observational guidepost to a deeper, more complete theory of reality. For a scientist, that's the ultimate prize. Ultimately, the enigma of the Eridanus Supervoid serves as a powerful and humbling reminder of the frontiers of our understanding. For decades, the lambda cold dark matter model has stood as the towering achievement of modern cosmology, a comprehensive framework that elegantly explains the universe's composition, its expansion history, and the growth of its large-scale structure. This model, often called the standard model of cosmology, posits a universe dominated by dark energy, represented by the Greek letter lambda, and cold dark matter, which provides the gravitational scaffolding for galaxies. It has passed test after test with flying colors, from the precise patterns of the cosmic microwave background to the observed distribution of galaxies. It is a resounding success story. Yet, the supervoid and its associated cold spot present a quiet, persistent anomaly that this otherwise brilliant model struggles to fully accommodate. The sheer scale of the void pushes against the predicted upper limits of structure size from cosmic inflation, and the temperature of the cold spot is colder than our most sophisticated simulations can easily produce. This isn't a dramatic failure that topples the entire edifice, but rather a faint, persistent crack in the foundation, a suggestion that our map of reality, while incredibly detailed, might still be missing a few crucial contours. It forces us to ask whether we are seeing the limits of lambda CDM itself, a point where its smooth, statistical averages break down in the face of a single, extreme, and statistically improbable object. Perhaps the model is correct in its broad strokes, but requires subtle refinements when applied to the most underdense regions of the cosmos, where the effects of dark energy and evolving gravitational fields might be amplified in ways we haven't yet calculated. The potential resolutions to this mystery branch out in profoundly different directions, each with its own implications for our fundamental laws of physics. If future data from observatories like Euclid and the Vera C. Rubin Observatory ultimately confirms that the supervoid is indeed the sole cause of the cold spot through a slightly enhanced integrated Sachs-Wolf effect, it would be a monumental triumph. It would demonstrate that lambda CDM is even more robust and versatile than we imagined, capable of explaining the most extreme environments the universe can concoct. We would have to refine our understanding of void evolution and the intricate interplay between dark energy and these vast emptinesses, but the core principles would remain intact. The universe would be shown to operate according to the known rules, just on a grander and more complex scale than we had previously tested. This outcome would solidify our current paradigm, allowing cosmologists to move forward with even greater confidence. However, the more thrilling possibility is that the data leads us beyond our current framework. If the void is confirmed but its gravitational influence is deemed insufficient to create the cold spot, we are forced to consider more exotic physics. One compelling avenue is a modification to Einstein's theory of general relativity itself. While GR has been exquisitely tested in the solar system and in strong gravitational fields, its behavior on the largest cosmic scales across billions of light-years is less certain. Theories like modified Newtonian dynamics or MUND and its relativistic extensions propose that gravity behaves differently in extremely weak field environments, such as the interior of a supervoid. Perhaps the rules of gravity change subtly in the great cosmic deserts, leading to enhanced redshifting effects that our standard equations don't capture. This would be a revolutionary shift, demanding a new theory of gravity that reduces to Einstein's in familiar territory, but diverges in the realm of the ultra-diffuse. Another profound possibility is that the cold spot is not a late-time effect at all, but a primordial one, pointing to a dramatic event in the universe's infancy. The concept of cosmic texture, a type of topological defect, is a prime candidate. If such a knot in spacetime exists, it would be a direct relic from a phase transition a fraction of a second after the Big Bang. Its intense gravitational field would have imprinted the cold spot directly onto the CMB, making the supervoid a secondary or even coincidental feature. Discovering evidence for cosmic texture would be like finding a fossil from the first moments of creation, providing direct observational insight into physics at energy scales a trillion times higher than we can reach with particle colliders. It would validate aspects of grand unified theories and illuminate the fundamental symmetries that shape the newborn cosmos. And then there is the most speculative yet intellectually captivating idea of all, the multiverse. While currently untestable in a conventional sense, the cold spot has been proposed by some theorists as potential evidence of a collision between our universe and another, bubble universe in a wider multiverse. The energy released at the boundary of such a collision could have left a distinct circular imprint on our CMB. While this remains a fringe hypothesis, its consideration highlights the extraordinary depth of the mystery. The supervoid forces us to entertain possibilities that were once purely philosophical, pushing cosmology into realms where the very definition of reality is up for debate. Whatever the final explanation may be, the Eridanus Supervoid stands as a celestial sentinel at the edge of our knowledge. It is not a problem to be solved so much as a guidepost pointing toward the next great revolution in our understanding of space, time, and the cosmic order. Its immense silence speaks volumes, reminding us that the universe is always more strange, more wonderful, and more ingeniously constructed than we can possibly imagine. Far from being a bizarre anomaly, the Eridanus Supervoid is actually a fundamental feature of the cosmos, a natural and essential part of the universe's grand architecture. To understand its true role, we need to see it not as an isolated emptiness, but as one of the titanic chambers in the vast, interconnected structure known as the cosmic web. This web is the largest pattern in existence, a luminous skeleton of matter that traces the distribution of both ordinary atoms and the invisible dark matter across the universe. Its brilliant strands are the galaxy filaments, immense rivers of thousands of galaxies flowing alongside one another, bound together by gravity over billions of light years. Where these filaments cross, they create dense, brilliant knots, the galaxy clusters, the bustling metropolitan centers of the cosmos, each containing hundreds or even thousands of galaxies swarming in a tight gravitational embrace. And stretching between these radiant strands and knots are the voids. These are the great cosmic bubbles, the empty spaces that give the web its name and its structure. The cosmic web is not a flat tapestry. It is a truly three-dimensional sponge where the bright filaments form the walls of the bubbles and the voids are the cavernous interiors. Without these voids, the filaments and clusters could not exist. They are two sides of the same cosmic coin, born from the same primordial seeds and evolving together over the entire history of the universe. The Eridanus Supervoid is simply the most spectacular example of this universal building block, a chamber so colossal it pushes the very definition of a void to its absolute limit. Its existence underscores a profound truth about our universe. It is not a uniform soup of evenly scattered galaxies. It is a place of extreme contrast, of dazzling cities of light and deserts of profound darkness, all woven together into a single, coherent structure that tells the story of gravity's work over billions of years. The formation of this intricate web was set in motion by the faintest of whispers from the birth of the cosmos. The initial blueprint was imprinted onto the universe in its first fleeting moments during the period of rapid expansion known as inflation. Tiny quantum fluctuations, ripples in the fabric of spacetime itself, were stretched to astronomical sizes. These ripples represented minute differences in density. Some regions were ever so slightly denser than others. After the Big Bang, gravity began to act like a cosmic amplifier on these imprints. Over hundreds of millions of years, the slightly denser regions had a stronger gravitational pull, drawing in more and more matter from their surroundings. They grew denser still, eventually collapsing to form the first stars, galaxies, and the vast filaments that connect them. Meanwhile, the slightly less dense regions lost the cosmic tug-of-war. As matter was pulled relentlessly toward the growing filaments and clusters, these underdense regions were gradually evacuated, becoming ever emptier. The Eridanus Supervoid is the ultimate result of this process in one particular region of space. It is the descendant of one of the largest primordial underdensities, a region that started with a tiny deficit and had that deficit magnified by gravity's relentless action across 13.8 billion years. It's not that nothing is happening inside the void. It's that the dominant gravitational story here is one of evacuation and expansion rather than accumulation and collapse. This is why the void and the surrounding web are so deeply intertwined. The same gravitational forces that built the brilliant walls of the Eridanus Supervoid are the very forces that carved out its immense interior. They are a matched set, a single structure whose form reveals the history of the universe itself. The relationship between a void and the web around it is not a static one. It is a dynamic and continuous gravitational dance. The dense walls of galaxies that surround a void like Eridanus exert an immense gravitational pull. This pull does two things simultaneously. First, it acts as a container, helping to define the void's boundaries and preventing it from simply dissipating into the general expansion of the universe. Second, it actively pulls any remaining galaxies and gas out of the void's interior like a cosmic vacuum cleaner, making the emptiness even more profound over time. This creates a fascinating flow of matter. Galaxies that reside near the edge of a supervoid often show a subtle but measurable motion, flowing away from the void's center and toward the dense filaments. This movement, known as peculiar velocity, is a direct consequence of the void's underdensity. The gravitational hill is so shallow at the center that everything naturally rolls downhill toward the steeper gravitational slopes of the surrounding web. This dynamic is crucial for understanding the void's evolution and its potential effects. A void is not a permanent, fixed hole. In a universe without dark energy, the gravitational pull from the surrounding web might eventually refill these empty regions over many billions of years. But in our accelerating universe driven by dark energy, the fate of the supervoid is different. The repulsive force of dark energy works against gravity's pull, causing the void to expand and become even emptier over time. This ongoing evolution means the Eridanus Supervoid is an active participant in the cosmos, a structure that is still changing and whose gravitational influence is still shaping the flow of matter and light around it. It is a grand cosmic process unfolding in slow motion, with the void and the web locked in a gravitational embrace that will continue for eons to come. To truly appreciate the scale of this structure, we can use a simple but powerful analogy. Imagine the universe as a range of towering mountain ranges separated by immense flat valleys. The galaxy clusters are the highest, most dramatic peaks where matter is concentrated at its densest. The galaxy filaments are the rugged mountain ridges and foothills that connect these peaks, still teeming with life but not as densely packed. And the voids are the great flat valleys between these ranges. A typical void might be like a wide, open plain, but the Eridanus Supervoid is different. It is not a valley, it is a continent-spanning basin, a depression so vast and so flat that its scale defies ordinary geography. If our local group of galaxies, which includes the Milky Way and Andromeda, were a small village, then a typical galaxy cluster would be a sprawling megacity, and the Eridanus Supervoid would be an entire, largely uninhabited continent. This perspective helps us understand its role. Just as valleys and plains are essential components of Earth's landscape, providing space and context for the mountains, cosmic voids are integral to the universe's topography. They are not mere empty background, they are active regions whose low gravity influences the dynamics of the entire system. The light from distant galaxies must travel through these valleys, and their shape subtly bends that light's path. The evolution of the web itself is governed by the gravitational interplay between the dense peaks and the empty basins. The Eridanus Supervoid, in all its immense emptiness, is therefore one of the pillars of the cosmic web, a defining feature that gives the universe its large-scale structure and its breathtaking beauty. The story of this cosmic mystery truly begins in 2003, a pivotal year when scientists working with data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, released the most detailed all-sky map of the cosmic microwave background ever created. This wasn't just another picture, it was a foundational document of our cosmos, a baby picture of the universe. Researchers immediately began analyzing this map, expecting to see the predicted random fluctuations, the tiny hot and cold spots that were the seeds of all galaxies. But one feature stood out like a sore thumb. In the southern celestial hemisphere, nestled near the constellation Eridanus, was a vast, diffuse region that was significantly colder than any model had predicted. The sheer size of this cold spot was the first shock. It spanned an area of the sky many times larger than the full moon. Initial calculations suggested the odds of such a large and cold anomaly appearing by pure chance in our standard model of the universe were less than 1 in 100. This wasn't just a curiosity, it was a potential crisis. The scientific community's response was a mixture of intense excitement and healthy skepticism. Could this be a simple error, an artifact from our own galaxy, perhaps a cloud of cold dust casting a shadow? For years, teams around the world worked to rule out every possible local explanation. They meticulously modeled foreground emissions from the Milky Way and searched for any instrumental glitches in the WMAP data. One by one, these mundane explanations were eliminated, leaving the cold spot as a stubborn, real feature of the deep universe. A decade later, in 2013, the mystery deepened and solidified with the arrival of data from the European Space Agency's Planck satellite. Planck was WMAP's more sensitive successor, equipped with instruments capable of measuring the CMB's temperature and polarization with unparalleled precision. When the Planck collaboration released its own exquisite all-sky map, all eyes turned to the southern sky. There it was, confirmed in stunning, irrefutable detail, the Eridanus cold spot. Planck's data not only confirmed its existence but also refined its properties, showing it was even colder and more coherent than the WMAP data had suggested. The probability of it being a random fluctuation now dropped to less than 1 in 200. With 2 independent space missions confirming the anomaly, the conversation in cosmology shifted dramatically. It was no longer a question of if the cold spot was real, but what could possibly cause it. The stage was set for a radical hypothesis, one that would connect this ancient imprint on the first light of the universe to a structure in the modern cosmos of almost unimaginable scale. The year 2015 marked a major turning point. A team of astronomers led by Istvan Shapudi at the University of Hawaii made a bold proposal. They suggested that the cold spot was not a flaw in the CMB itself, but a shadow cast by a colossal cosmic structure between us and the primordial light. Their hypothesis was the Eridanus Supervoid. Using data from the Pan-STARRS telescope and NAS, a wide-field infrared survey explorer, they pieced together a 3-dimensional map of galaxies in the direction of the cold spot. What they found was a staggering emptiness. Their analysis pointed to a region nearly 2 billion light-years across that was strikingly underdense, containing far fewer galaxies than any other volume of similar size. This was the first direct observational evidence linking the ancient cold spot to a modern physical structure. The proposed mechanism was the integrated Sachs-Wolf effect, but with a twist. They argued that the sheer, unprecedented scale of this supervoid meant that the standard rules might not fully apply. The cumulative energy loss for light traveling across such a vast emptiness could be the key to explaining the unexpected cooling. The publication of this paper sent ripples through the astrophysics community, transforming the cold spot from an abstract statistical anomaly into a tangible cosmic puzzle with a proposed testable cause. This hypothesis ignited a new phase of discovery, the era of targeted observational campaigns. Astronomers around the world began pointing their most powerful telescopes at this patch of sky, not to look at bright objects, but to meticulously map the nothingness itself. The Dark Energy Survey, a ground-based project using a massive camera in Chile, began dedicating significant observing time to this region. Its goal was to measure the precise shapes and redshifts of millions of faint galaxies to build a high-resolution map of the supervoid's true shape and depth. Was it a single spherical void or a complex of smaller emptinesses? Simultaneously, other researchers began analyzing archival data from the Sloan Digital Sky Survey, re-examining the galaxy distribution with new statistical tools to confirm the underdensity. The results that came back were complex and in some ways deepened the mystery. Some studies confirmed the presence of a large underdense region, but suggested it might not be a single coherent structure. Others found that the proposed supervoid, while immense, might not be quite empty enough to generate the observed temperature drop through the standard physics of the integrated Sachs-Wolf effect. This discrepancy created a fertile ground for debate, pushing cosmologists to refine their models and consider more exotic possibilities. The timeline of investigation continues right up to the present day, with the launch of new missions designed to solve this and other cosmic mysteries. The European Space Agency's Euclid spacecraft, which began its operations in 2023, is a supervoid hunting machine. Its core mission is to create the largest and most accurate 3-dimensional map of the universe, precisely measuring the distances to billions of galaxies. For the Eridanus Supervoid, this means we will soon have a definitive census. Euclid will tell us the exact geometry of the void, its density profile from its near-empty center to its densely packed walls, and provide a precise measurement of its mass deficit through weak gravitational lensing. This data will finally answer the critical question: does the gravitational fingerprint of this void match the chill of the cold spot on the ground, the Vera Sea? Rubin Observatory, set to see first light in the coming years, will complement this effort with its own unprecedented wide-field survey, monitoring the sky for a decade to detect any subtle motions of galaxies flowing away from the void's center. This timeline of discovery, from a puzzling blotch on a map to a targeted international investigation, exemplifies the scientific method in action. It's a story of initial surprise, rigorous verification, bold theoretical leaps, and the relentless pursuit of better data, a process that continues to unfold as we speak, bringing us closer than ever to understanding the true nature of this colossal cosmic emptiness. From the illusion of a crowded night sky to the discovery of a cold spot on the edge of creation, our journey into the Eridanus Supervoid has taken us across the largest scales of space and time. We have traced the path from a puzzling temperature anomaly in the universe's first light to the identification of a cosmic desert, so vast it could swallow thousands of galaxies without a trace. This isn't just a story about a hole in the universe, it's a revelation about how the cosmos is structured, a lesson written in negative space. The great cosmic web, with its brilliant filaments and dense clusters, is defined as much by its empty chambers as it is by its shining cities. The supervoid is not an error or an absence, it is a fundamental feature of reality, a fossil from the quantum dawn of time that has been stretched to a scale that defies belief. Its profound emptiness is not passive. As Einstein's theory of general relativity dictates, the distribution of matter and energy is inextricably linked to the geometry of spacetime itself. Within this immense region of weakened gravity, the fabric of the cosmos is less curved, and because of this, the flow of time itself is theorized to run ever so slightly faster. We have explored how this isn't science fiction, but a direct consequence of gravitational time dilation. The same physics that makes the clocks on GPS satellites tick faster than those on Earth, just amplified across a billion light-year laboratory. This incredible link between the greatest emptiness we know and the fundamental ticking of the cosmic clock is perhaps the most profound takeaway. It shows us that the universe is a dynamic, interconnected, and deeply relational place. Our experience of time is not universal, it is local, shaped by the gravitational landscape we inhabit. A civilization born within the void would, over eons, chart a history that diverges minutely from our own, their timeline woven at a subtly different rhythm. This mystery has pushed the limits of our understanding, creating a vibrant debate at the frontier of cosmology. Does the supervoid fully explain the cold spot through an amplified integrated Sachs-Wolf effect? Or is its gravitational influence insufficient, pointing toward more exotic physics like cosmic texture or even a collision with another universe? The debate itself is a testament to a healthy, thriving science, one that is unafraid to confront its own uncertainties and question its foundational models. This is how knowledge grows, not through definitive answers, but through the rigorous collective pursuit of them, through the clash of data and theory that forces us to think bigger and dig deeper. The investigation is far from over. We stand on the brink of a new era of discovery, with powerful new observatories like the Euclid spacecraft and the Vera C. Rubin Observatory coming online. These are not just new telescopes, they are time machines and cosmic cartographers that will map the void's true shape, weigh its emptiness with precision, and finally determine its role in this grand cosmic story. They will test our theories with a rigor previously unimaginable, potentially confirming our standard model of cosmology or forcing a revolutionary shift in our understanding of gravity, dark energy, and the very first moments of the Big Bang. The enigma of the supervoid is a powerful reminder that the universe is still full of wonders waiting to be uncovered. It teaches us humility, showing that for all we have learned, we are still just beginning to read the story of the cosmos. So the next time you look up at the night sky, remember that the true majesty of the universe lies not only in the points of light you can see, but also in the immense, silent, and powerful emptiness between them. Stay curious, for the greatest discoveries are not behind us. They are waiting in the vast, dark, and beautiful unknown, beckoning us to look deeper and